This is 2011 FRQ number 2. This is still in the calculator portion. Okay, it says, as a pot of tea cools, the temperature of the tea is modeled by a differential function h between 0 to 10 minutes, where t is minutes and temperature is measured in degrees Celsius. Values of h of t as selected values are shown in the table above. So part A says, use the data above to approximate the rate at which so rate is the slope, right? Rate is the first derivative. Rate is y prime. So that's something you really want to catch, all right? The rate at which the temperature of T is changing at the time T equals 3.5. So 3.5 is right here, which means that I'm going to use these two for a slope and go y2 minus y1 over x2 minus x1 to approximate, all right? Hopefully by now you start to see some similarities. We do see some of these questions over and over again. So hopefully you will see that you're pretty much doing the same approach in these problems. All right, so you want the rate of change at t equals 3.5. So if you just write it out, you're really doing h of 5 minus h of 2. That's y2 minus y1 over x2 minus x1. All right. So you can explain what you're using without really having to write out what you're using. Okay, this gives me negative 8 over 3. So negative 8 over 3 degrees Celsius per minute. And that's it for part A. Okay, part B says, use the correct units to explain the meaning of 1 over 10 integral between 0 to 10 h of t in the context of the problem. Use a trapezoidal sum with 4 intervals to indicate by the table to estimate this integral. So first of all, we know this means average. When you have a value or a fractional value, 1 over something, 1 over the total x value or t value multiplied by the integral, you're looking for the average of something, right? And what does this give me? This gives me a total temperature, right, in over 10 minutes. So then if you are taking 1 over 10, you're looking for the average temperature in degrees Celsius over 10 minutes. So 1 over 10 integral of 0 to 10 h of t is the average temperature in degrees Celsius over the 10 minutes interval. All right, so now let's use the trapezoidal rule to get this. The trapezoidal rule gives us the integral. Since we don't have the equation for h of t, that's why we need to use trapezoidal rule to kind of help us figure that out. So now let's see. We have 1 trapezoid, 2 trapezoid, 3, and 4. All right, so let's find the integral first. 0 to 10 h of t equals, trapezoid is 1/2. What is the height? The difference between these two, and then base 1 plus base 2, 60 plus 66. Next trapezoid, these two, so 1/2 times the height, so 5 minus 2 is 3, and then base 1 plus base 2, 52 plus 60. And then 1/2, the height between these two, 9 minus 5 is 4, base 1 plus base 2, 44 plus 52. And then last but not least, the height between those two is 1, and then base 1 plus base 2. All right, again, this is the calculator portion, so if you plug it all in the calculator, you will get the integral to equal to 529.5. All right, and then don't forget you want the average of this, so 1 over 10 times 529.5 gives me 52.95 degrees Celsius. That's the average temperature over the 10-minute period. Okay. Part C, evaluate the integral between 0 to 10 of h prime of t. Use the correct units. Explain the meaning of expression in the context of this problem. So what does that mean? So integral of 0 to 10 h prime of t dt. All right, so it's the antiderivative, right? This is already h prime. So when you take the antiderivative, it's h of t evaluated 0 to 10, right? So plug in the 10, it's h of 10 minus h of 0. Well, h of 10 is 43 degrees. H of 0 is 66 degrees. So negative 23. So what does that mean? It means that after 10 minutes, the entire thing dropped down from 66 degrees to 43 degrees. It dropped 23 degrees. So the temperature dropped 23 degrees after 10 minutes. Okay. All right. At t equals 0, biscuits with temperature 100 degrees Celsius were removed from an oven. So initially these biscuits were 100 degrees Celsius. The temperature of biscuit at time is modeled by a differentiable function b, for which it is known that b prime is this function. Use a given model at time t equals 10. How much cooler are the biscuits than the t? All right, so t at the end of 10 minutes, right here, up here on my table, says t is 43 degrees. All right, so now I need to know after 10 minutes, how hot are these biscuits? All right, so biscuits, let me move this up. You need to see everything. Well, biscuits started with 100 degrees, right? And then after 10 minutes, B prime, that's how the rate at which its temperature is decreasing. Okay, so let's see, that's 100 plus what? Let's see what this integral is going to give me. So clear, sorry, math 9, negative 13.84 e to the negative 0.173 x, close your parentheses, comma x, comma 0, comma 10. Okay. All right, so that integral gave me a negative 65.17, which makes sense. Your biscuit is supposed to be cooling down, right? So while I still have that on my screen, I'm just going to add the initial 100 degrees. So right now, the biscuits are 34.183 degrees Celsius. All right, so the T is 43 degrees. So 43 minus 34.183. So I get 8.817 degrees. So the biscuit are 8.817 degrees cooler than our tea. Okay, that's it.